Okay. Are we good to start? All right. Okay. So I am excited to welcome everyone to day 2 of the CCAI Summer School 2023. I am Donna. I will be your lead TA, and I'm here with Danlin, who will be your support TA for today. And we would like to, before we start, sorry, trying to go backwards on my, before we start, I just want to say a tiny bit about Climate Change AI, which is a a volunteer initiative that catalyzes impactful work, but at the intersection of climate change and ML. And if you haven't already, you can learn more at www.climatechange.ai. You can follow us on Twitter at Climate Change AI. You can join, if you haven't already, the community platform, and you can subscribe to the newsletter. Okay, so for today's lecture, I'm going to direct you to the community platform to ask all your great questions, and you can ask it by going to the lecture Q&A space. So there is the community platform, and then within there, the CCAI lecture Q&A space. And once you're in there, you'll see where you can reply in the comment thread. And because there's so many people, and there'll probably be lots of great questions, we don't have time to answer them all. So questions that get more thumbs up will have a higher chance of being selected and asked to our speakers today. And it's very, very important that everyone abides by CCAI's code of conduct. If anything arises, please report it to reporting at Climate Change AI. So for today's schedule, we have our first speaker, Dr. Evan Sherwin, who's going to speak for about an hour on measuring progress under the Paris Agreement. Then we'll have a little break, and then we'll have another speaker, Dr. Kasia Tokarska, who will be speaking about AI for monitoring, reporting, and verification of corporate GHG emissions. And after that, we'll direct you to where you can find more information for the tutorial. All right, without further ado, let's get to our first speaker, Dr. Evan Sherwin, who will be speaking on measuring progress under the Paris Agreement. Dr. Sherwin, he has a lot of expertise in policy analysis. He is also postdoc research at Stanford in the Department of Energy Science and Engineering. He is also the founder and chair of the Methane Emissions Technology Alliance, and a founding member of the board of directors of CCAI. So I'm super excited to kick it off and hand it over to Evan. So I will stop, or Evan, you can go ahead and share, and I should be able to stop sharing. Go ahead.
Great. Thank you so much, Donna. So yeah, today I'll be talking about measuring progress under the Paris Agreement, which really just means measuring changes in greenhouse gas emissions in various jurisdictions and from different sectors over time. I'm Evan Sherwin of Climate Change AI in Stanford University. A bit about me: I consider myself a data and informed energy and climate policy analyst. I got my start at UC Berkeley as an undergraduate in physics and applied mathematics. Toward the end of that time, I got very interested in climate change and decided that I wanted to focus on really guiding decisions of technology deployment and how we sort of collectively bring the tools we have together as a society to address this major problem. And my first step in that direction was working as a consultant, mainly for government agencies, doing mathematical modeling of energy systems at a company called Lumina Decision Systems for about 3 years. Really enjoyed it, and decided that if I wanted to keep going in that direction, I should probably get a PhD. To do that, I went to Carnegie Mellon University in the Department of Engineering and Public Policy and worked in the Climate and Energy Decision-Making Center with Professor Inés Azevedo. Had a wonderful time. And every project I worked on, I realized, in order to actually answer important questions, I need to learn more statistics. And if you pull on that thread hard enough at Carnegie Mellon University, you can get an extra master's degree in machine learning, which is the direction I went. And right toward the end of my PhD, I was crunching away on my thesis and was invited by my fantastic colleagues, particularly Priyadonti and Lynn Kak, to get involved with essentially what became climate change AI. And I'm so glad I did. And I've been part of the team ever since. That was back in 2018 that we sort of started in the embryonic stages, and it's been really exciting to see what the organization has become. And finally, I 4 years ago started at Stanford University in methane science in particular, which is a lot of what I'll be talking about today, but certainly not all. So my research focuses on the role of hydrocarbon fuels in a net zero future. And that might sound a bit like a paradox, but really the energy system we have today uses a lot of hydrocarbon fuels, oil and gas, and so forth. And even if the goal is to transition entirely away from those fuels, or mostly, we're probably going to use quite a bit in the meantime, and we really ought to make sure that we reduce emissions in the process as we do that. So I consider really all my work to be energy and climate decision focused research, much of which is focused on methane emissions, which includes field work, literally going out into various remote locations and testing out methane sensing aircraft and satellites and ground-based sensors. Also taking data from these enormous surveys that are happening of large areas with these technologies and translating them into meaningful insights, like how much methane is coming from the oil and gas system in a given region, or how much does emission intensity vary across different companies. I also do a fair amount of energy systems modeling. So this includes what's called techno-economic analysis, basically estimating how much something that doesn't exist yet is going to cost, or a change in operation of a system would cost. That also is often combined with systems dynamics modeling, sort of engineering systems modeling. Much of the time that includes optimization and really understanding uncertainty. The third area is machine learning, a fair amount in the remote sensing side, deeply connected with machine learning, data discovery, finding useful information from sort of diffuse information. I'll go more into this in a bit. And then community building. When I say that, it's not some technical term. It's literally working with climate change AI to help build a community at the space at the intersection of climate change and AI. Much of what I'll be talking about today is on the methane side, but also the machine learning side. And I will also talk about some other gases, because of course there are quite a few that are relevant. So the title of this talk is Measuring Progress under the Paris Agreement. And really, maybe this is too cursory a treatment, but the Paris Agreement of 2015 was a legally binding treaty, with the first of its kind, to attempt to commit to a limit in global warming, either 2 degrees C or preferably 1.5 degrees C above pre-industrial temperatures. And the language in here, while countries aim to reach global peaking of greenhouse gas emissions as soon as possible and a climate neutral world by mid-century. All right, well, if that's a commitment to have greenhouse gas levels from all the relevant countries reach the maximum that they ever will at a given point, and go all the way down to net zero by mid-century, then we need a really good way of tracking those emissions and making sure that those goals are met, which is really what I'll be talking about. So the big questions: how do we track progress? Where do we need better methods for tracking progress in terms of emissions? And how can AI and machine learning help? So I'm going to start things off with a poll. Which of these listed gases are greenhouse gases? So the poll should go out, and I'll give a few minutes for responses before going to showing the results. And this is also a good time. maybe this is early for questions, but if there are any questions, then feel free to start now. And I should say, well, so what is some of these? These are chemical abbreviations. AR is argon. F gases are refrigerants, or largely used as refrigerants, fluorinated gases, such as hydrochlorofluorocarbons and so forth. CH4 is methane. H2O is water. H2 is hydrogen gas. O3 is ozone. N2O is nitrous oxide. N2 is nitrogen gas. O2 is oxygen. And C2 through C4, that's a slightly different convention, but those are hydrocarbons with 2 to 4 carbons in them. So C2, that's generally ethane. C3, propane. C4, butane. And I see something in the, good. So yeah, let's give this another minute or so. And if there are any questions, we can go to those right now. Another, if we're not there yet.
There are no questions currently that I can see.
Oh, good.
But
25 then from the
yeah.
poll.
But I'm curious if I can ask one question about how much of your in your learning you had to, like, how much of learning chemistry was that a barrier to understanding the policy and ML work that you do?
It was
Or is it a lot of chemistry?
Yeah, the more I go in this direction, the more chemistry I need to learn. It's not my primary area of expertise, but it's really, yeah, it's come up time and again in different aspects of what I've been doing. In particular, something that I had not been on my radar at all until a couple months ago is that methane is, in fact, a significant atmospheric precursor to tropospheric ozone. So ozone, this is O3, and depending on where it is in the atmosphere, its effects are different. You know, there's the ozone layer up in the stratosphere, which is really critical for shielding us from harmful ultraviolet. But in the troposphere, more closer down, and then ground level. So if humans can breathe it, basically, ozone can be a real health damaging air pollutant. And the health impacts from a recent United Nations study, the health impacts of ozone formation as a result of methane emissions are much larger than I had ever imagined. It's responsible for a substantial number of deaths and substantial illness every year. So I definitely would say for anybody digging into the energy and climate space, particularly looking at greenhouse gas sensing, an understanding of chemistry, and also an understanding of the spectral signature of different molecules is really important. So for a lot of remote sensing, the way that it works, you're looking down from above, usually at something, and you want to see it. The way that we can see methane is basically because it absorbs certain frequencies of light and not others as much, and you can kind of do differencing. That might be too long an answer, but those are some ways chemistry can be useful. So shall we go to the poll results?
Can you see my screen right now? I'm showing there's 81 responses and counting.
No, I'll stop my share. Maybe
Okay.
there we go. Oh, wonderful. Okay, very good. So, all right. So, excellent identification of carbon dioxide and methane. Argon is not a greenhouse gas. That's fairly inert. Yes, ethane, propane, and butane are not commonly talked about, but do have a substantial greenhouse effect. It's in over a 100-year time frame. It's about half of what methane is, a little less in some cases. The F gases, yes, refrigerants are powerful greenhouse gases, which is why end-of-life recycling for air conditioners and similar appliances is Absolutely critical. Hydrogen gas is not a direct greenhouse gas, but indirectly it is, as in the, well, coming back again to chemistry, the interactions that hydrogen has as it breaks down with other molecules in the atmosphere results in a pretty significant net warming effect. Nitrogen gas is not a greenhouse gas. That's quite inert in the atmosphere, as is oxygen gas. Ozone is a greenhouse gas to some extent, and water vapor is arguably the most powerful greenhouse gas, in fact. So very good. This is excellent to see. And yeah, so that's now that we've gotten started, let's dig into how we keep track of these different gases. So and how much they affect the overall picture. Here is a breakdown of 5 of the most significant greenhouse gases in the atmosphere, or greenhouse gas classes in some cases. If we're looking at a 100-year time scale, and the time scale matters because many of these molecules decay quite quickly in the atmosphere. Some of them last a really long time, like carbon dioxide. So the amount of warming that one gets over a 20-year period is different than over a 100-year period. If we're comparing carbon dioxide to methane or nitrous oxide or something else. So carbon dioxide on a 100-year timescale is the bulk of the total. A lot of it's from anthropogenic, from fossil CO2, some of it's from land use. Methane's substantial, it's pretty large, and nitrous oxide from, for example, agricultural activity and a few other things matters. And the F gases they're mighty, but thankfully they're not a huge part of the whole picture, although we can't ignore them. If we look at a 20-year time scale, methane becomes a much larger fraction of the total. So there's a lot of debate over what timescales we should be thinking about. And I should say these are global numbers from the Environmental Protection Agency's greenhouse gas inventory. And even these numbers, there's a lot of discussion over what they're continually undergoing refinement. So how do we measure and estimate emissions of these different greenhouse gases? There are 4 major ways, in my view, that we do this, and there's more nuance there, but one is physics and chemistry first principles, really just based on our understanding of how a given process works. For example, at a power plant, we know when we combust a fossil fuel, then it turns into carbon dioxide and some other products. And we've got a pretty good handle on how that works. So if we know how much fuel went in, we've got a pretty good sense of how much carbon dioxide came out. Another is direct measurements at everywhere that there might be emissions in a given sector. And that's feasible in some cases, but in other cases, it's pretty difficult. Emission factors are another approach that one can use. And this is estimation based on a small set of measurements taken in one or a few locations and then extrapolated based on some engineering understanding, sort of some scientific understanding to a broader area. And then there's model-based simulation using atmospheric measurements. Physics and chemistry first principles, again, if we have a natural gas-fired electric power plant, then if we're combining carbon CH4 methane with oxygen in the air, we know what that does. We know what that produces: water, carbon dioxide, and we can keep track of emissions pretty well that way, as long as we know the fuel input. Direct measurements at all facilities is something that basically happens in many countries, such as the United States, at power plants. There are continuous emission monitoring systems that initially were put in place in many cases for air quality, looking at sulfur emissions and nitrous oxide, particulate matter. But many of these also include carbon dioxide sensors, and this is extremely valuable for just knowing how much carbon dioxide is coming from power plants, some industrial facilities, anything that's got sort of tailpipe, a smokestack, where you can just measure, all right, that's where the emission source is. But we can't do this everywhere. This doesn't exist in many countries, even at power plants, and in much more distributed facilities, it just isn't always feasible. So emission factors, this is sometimes called bottom-up estimation, is another method that we can use to estimate emissions, especially if there are a lot of small distributed sources. And the way that this is generally done is it starts off with a relatively small number of measurements. Hopefully that's representative of the larger thing that we're trying to estimate emissions from. And then we just scale up those measurements as a population estimate, and government emission inventories estimates, so those numbers from the Environmental Protection Agency, essentially use this type of approach. And to put a slightly finer point on it, an example is for oil and natural gas methane emissions. The emissions inventories are largely based on a series of studies that were conducted counting the number of components that there are, how many valves are there, how many open-ended lines, how many flanges are there on a wellhead in the average well in the United States, or in some wells that researchers had access to and were able to go and count, and then how many of those, or what fraction of those, are leaking. How big are those leaks that are detected, and how many wellheads are there in the United States? Then you can essentially do a big exercise in addition and multiplication to get an estimate based on that relatively small sample of measurements of components of what emissions are for this type of equipment. Or if you have all the types of equipment that there are in oil and gas production, you can get an estimate of total emissions from oil and gas production. Another approach, this atmospheric model-based regional simulation using atmospheric measurements. There are different ways to do this, from satellites, from aircraft, from towers that are on the ground. This is two figures from a recent study by my colleague Daniel Varon over at Harvard, who took measurements from a satellite called the TROPIMI instrument on the Sentinel-5P satellite, which is able to estimate methane concentration enhancements using essentially using the wavelengths of light that methane absorbs particularly in, and then combines that along with some assumptions about the distribution of where potentially methane emitting infrastructure is, and what the winds are and so forth, to estimate methane emissions. Basically turn this map of estimated concentration enhancements into this map of estimated emissions from oil and gas production. In this case, well, this is a region of Texas and New Mexico where most methane is coming from oil and gas. And this can be extremely useful, especially in places where we just can't take measurements, because sometimes it's very difficult for a variety of reasons to collect measurements directly. So remote sensing can be very valuable, but it does require a fair number of assumptions, and there's uncertainty as a result of that, as there is with most of these methods. So I'd like to pause here, and I want to try this out. There's a Google Doc that everyone should have access to. It's available in the live stream. Is that right?
Hold on one second. I'm gonna check on that.
So what I'd like to do is to have everybody have a couple of these group brainstorming sessions where just everyone can get their thoughts down on paper and really just get thinking about these different about some of these questions.
This is great. Can you just resend the link into the Zoom chat, and then that would be really helpful.
Absolutely.
Thanks. And while that's getting up, and while we're posting it to the live stream, do you want to take a question? There's a couple of questions.
Yeah, I would love to.
Okay, So yeah, go ahead and post that and then I will shoot you a question.
Great.
So I will ask a question that was posted by Arjit Goswami. My apologies, Arjit, if I'm mispronouncing your name. And the question is about sometimes the being able to, okay, and the doc has been shared now. Okay, so the question is about, can AI models predict where geographically will the effects will be felt by certain, like in terms of certain climate change impacts? Can you predict where they will happen? And an example given is how CFCs led to an ozone hole, but it was over Antarctica, and it didn't match up with the people who were producing those chemicals weren't in Antarctica. Yeah, so can you speak a little bit about that, being able to predict where the effects will land and that kind of matching up of the source to the impact?
Absolutely. So for understanding impacts, for predicting the future in a way that's not going to look like the past, generally what that requires is a more fundamental understanding of the science of the system one is modeling. So if we want to understand the impacts of the geographic distribution of impacts of greenhouse gas emissions in a given location or of a given type, then generally the most effective tools there are atmospheric and climate simulation models, which require a fair amount of sort of the physics baked into their operations. The main ways that machine learning can be valuable, in my view, and in that type of modeling, is less in informing the types of results that they give and more in speeding them up. So many of these machine learning, or many of these atmospheric simulation models are extremely computationally intensive. And if it may not be possible in some cases to run a lot of different scenarios just because of how resource intensive they are. But it's possible in many cases to develop a machine learning sort of surrogate of a very computationally intensive model that produces, given the same inputs, produces pretty similar outputs, but runs 10, 100, 1,000 million times faster. And maybe not a million, but many times faster. So that, I would say, is one application where AI could be very useful. But in general, AI is very good at predicting what's going to happen under conditions that are similar to what it's able to be trained on. And if the goal is to predict something that looks really different than any data that we can give the model, as in predicting a fundamental change in the climate, then AI itself tends to have difficulty with that type of problem.
And lots of answers are coming in to the Google Doc.
Awesome. So great. So oh, cool. People are adding questions too, biases and limitations. Should I? Yeah, I guess I'll just share my whole screen. And that way, if I toggle to to the Google Doc, then people can see that too. So yeah, so some assumptions that underlie the models. There's an assumption that the tools exist in the area we're looking at. Absolutely. That sometimes the technology export limitations or the cost is prohibitive for deployment of a given technology in a given region. Spatial resolution of emissions estimates can vary, quite a lot. The closer you get as a rule to an emission source, the more precise one can be, but it can be more difficult to survey a large area. One assumption is all the sensors are giving us data that's efficient, and yeah, that's not always the case. Bottom-up estimates yeah, are we estimating based on data that's representative of the population? This is so critical. I know that this is climate change AI, but I feel like just some of the fundamentals of statistics are some of the most important things in many of these, solving many of these problems. Chemistry in the open atmosphere can change. Yeah, and it can, in some cases, make gas tracking difficult. Many of the greenhouse gases, essentially the reason a lot of the greenhouse gases are greenhouse gases is because they're pretty stable in the atmosphere, at least over time scales of atmospheric transport. So days, weeks, months. But some of them are not. They're indirect greenhouse gases like hydrogen, which pretty quickly interacts with other molecules in the atmosphere and turns into other gases, which are greenhouse gases. So that's certainly the case. Temporal and spatial resolution. Yep, those are really important factors. Yeah, methane. So the methane, there's a question of anthropogenic versus non-anthropogenic emissions, because there certainly are substantial emissions from wetlands, which are, it looks like, increasing. And there are big questions over whether that can be considered anthropogenic or not. Ground truth validation can be difficult. We'll talk about that in a bit. Good. So these are wonderful answers, and please feel free to keep writing, and we can revisit these in a little bit. I'm really happy to see folks engaging on this front. Yeah, in the interest of time, I'll keep on going. So which methods do we use for which sources? Carbon dioxide. In general, emissions inventories are, I think we have a pretty good understanding of anthropogenic carbon dioxide emissions, particularly from fossil fuels, from industry, just because we understand these industrial processes. We understand, as I mentioned before, when we burn a given amount of fuel and we produce a given amount of cement, what the carbon dioxide that results from that is. And there's a little uncertainty in how much fossil fuel is actually used, and there's uncertainty in the global broader carbon cycle. And this figure to the left is from the Global Carbon Project, Friedlichstein et al. From 2020. This is looking at the different sources and sinks of carbon dioxide. So there's some uncertainty there, absolutely, but we've got a reasonably good sense of what's going on. With methane, there's a lot more uncertainty. So this is also from the Global Carbon Project, Sunwa et al. 2020, and you can see that there are these sources tend to be much more diffuse. We're talking about wetlands, fossil fuel production and use. There are more than 1 million oil and gas wells in the United States alone, as opposed to a much smaller number of power plants. Agriculture and waste is very diffuse, and so forth. And we can see here there are what are called bottom-up estimates, and these are those sort of scaling up from a small number of measurements. And then there are top-down estimates, which are these more regional estimates based on atmospheric methane concentration measurements, and that those have a harder time sort of resolving exactly what the source of a given type of methane is, if there's agriculture and oil and gas production in a given area. But there can be pretty big differences between the top-down estimates and the bottom-up estimates. So there's a lot we don't know still about methane, and a lot of work to be done to really put a finer point on what emissions are. And I should say the left is anthropogenic, and the orange and the right is natural fluxes in both directions, so emissions and sinks. So F gases, hydrogen, and slightly heavier hydrocarbons. I would argue we don't know nearly enough about how much of these are emitted. We really need a better handle on what fraction, when an air conditioner or a heat pump or a refrigerator is retired, what fraction of the refrigerant is actually destroyed, as it, at least in the United States, should be, and how much of it's just vented into the atmosphere, which is a lot easier in a certain way. Those numbers make a big difference on a lot of fronts, especially if the goal is to switch heating in many regions over to heat pumps. We really ought to figure this one out. Hydrogen emissions from there are hydrogen systems today, especially around oil and gas production and refining, mainly refining activity. And there's a lot of discussion about really scaling up hydrogen, mainly low carbon hydrogen, for a variety of applications. It's a small molecule. It can be difficult to handle. It can be difficult to detect. There's important work going on in this direction of understanding emissions from hydrogen systems for moving hydrogen around in trucks and pipelines and so forth. But there's, in my view, a lot more that we really need to understand. And emissions of volatile organic compounds, which again are both greenhouse gases and pretty significant human health damaging air pollutants. There's a lot more, in my view, that we really do need to be looking at, because natural gas, especially at sites of production, it's not just methane and carbon dioxide and other inert gases. There's a fair amount sometimes of these heavier hydrocarbons, and if there are emissions, then those are going into the air and into the air that we breathe. So these are some areas that I think are really, really important for future research. And of course, there is ongoing research there. And just kind of to summarize, we've got a few examples of where we use these different methods for different cases. So electric power plants, those are big sources of carbon dioxide, and really there one could use all the methods here, but the main methods, engineering first principles, work pretty well for power plants. Universal direct measurement with continuous emissions monitoring systems, those are present in many cases in the United States and in some other countries, not in all countries. And emission factors, those work fine for countries that don't have continuous emissions monitoring systems. At least they work fine in a lot of cases. Oil and gas facilities, first principles, it's more difficult because there's a lot that just, something springs a leak. It's hard to model that using engineering first principles or physics and chemistry. In some cases, there is universal direct measurement. For example, comprehensive aerial methane surveys, which I'll talk about a little bit, are that's a way to measure everything in a given region. Not at a huge, you won't be able to necessarily tell which component is leaking, but you can tell which facility is emitting. Emission factors are very common, and the regional simulation is also very common for oil and gas facilities. For wetlands, the first two are really tough, and emission factors are quite common. There's regional simulation as well. Wetlands are a difficult area, and we really need more on the ground data, especially in the tropics, where a substantial amount of wetland methane activity is. Forests, carbon dioxide and methane, it's largely emission factors and regional simulation. Universal direct measurement would be very difficult. And for air conditioners and hydrogen infrastructure, I would say maybe I can be a little more generous, but there's a lot of work to be done on that front. So as a recap, I believe this was within an earlier lecture, but maybe the curriculum's changed a little bit since last year, but at its core, for the purposes of this lecture, all anyone needs to know about machine learning is that you take an input, some sort of input data or sets of input data, and an output that you want to be able to predict. And machine learning, AI, almost synonyms, not quite, puts out a program that produces the output from the input. So as a brainstorm, which I think some have already gotten started on, how can AI be used to help with greenhouse gas measurement? Oh, this is cool. So here we've got automated detection of methane emissions from satellites. Absolutely, we'll be talking about that in very, very shortly. Sharing awareness to people to teach them about climate change, because most of the people don't know about climate change, and they're willing to help eliminate it. For raising awareness, absolutely, AI can be used there, and especially to help find out sort of, what types of messages might be most useful for different types of different audiences. AI can help the data collection process, reducing the need for manual data entry and improving efficiency. AI-powered drones and robots can help collect data in real time from specific locations, enabling more frequent and accurate measurements. Yeah, so AI for figuring out where it makes the most sense to measure, which sites might be the highest emissions. That's a very promising area that there's been some really good work in from in particular Lira Wang, formerly of Harrisburg University, now at UT Austin, won the Best Paper Award in the NeurIPS 2020 tackling climate change with machine learning workshop for work precisely along those lines. The AI can analyze which locations are major contributors to climate change and put sanctions on the governments of those areas. So certainly, yeah, AI can figure out where some of the AI can analyze and help with pattern recognition. I'd be pretty nervous if we just had a pure AI algorithm determining what emissions are in a given place, but it could certainly help us flag some of the bigger areas. I think we're gonna really want to, especially if someone's gonna start going in the direction of sanctions, we need an extremely robust approach to really say what emissions are in a given area. The question of sanctions is that's above my pay grade, but we've so identifying areas where greenhouse gas emissions are emitted, even small emissions, yeah, that absolutely. Accurate prediction in the planned phase of production of a manufacturing plant or factory. AI can predict how much greenhouse gas will be produced in specific operational parameters, help make adjustments. Yeah, so AI can be useful in even figuring out design of factories. You'd need I have to think more about how exactly to implement that, but so this is wonderful. I wish I could.
Dr. Sherwin, can I interrupt you with just some clarification questions on behalf of the group?
Absolutely, yeah.
So two things that you mentioned that not everyone may be familiar with. Could you tell them or tell us what is an emissions factor, and also when you say first principles, what? Sure. Go back over that again. Thanks.
Yeah, maybe I went too quickly over that. So when I say first principles, what I mean is we know the chemical equation. I can go back to the slide. I think it's slide here. We know the chemical equation of what happens when methane is combusted. So if we've got a natural gas power plant and it's burning CH4 methane, then it's gonna react with oxygen plus some heat, and it's gonna produce hydrogen, or produce water and carbon dioxide. So that's a first principles approach, in that we don't need to know anything about the power plant. We don't need to know anything about the incoming fuel other than that it has methane in it. And as long as we know how much natural gas is being consumed by the power plant, and assuming that it's operating properly and the combustion is working along this these lines, then we know exactly, we know how much carbon dioxide is being emitted. So that's an example of first principles. We don't need to measure anything. We don't need to know the details of the power plant. All we need to know is the basic chemistry in this case. For emission factors, so this, it's a little bit more of a nuanced idea, but the idea here is that suppose there's a big area with a lot of oil and oil wells, as an example. And we wanted to estimate what the emissions are of this whole field of oil wells. If we don't have the budget to go and measure everything, then we might just want to estimate, well, what does the average oil well emit? So that's basically what an emission factor is. An emission factor is we go out and measure some small number of facilities and estimate what emissions are for sort of a representative facility, and then we just take that number and multiply it by the number of the oil wells in this case, and that gives us an estimate of emissions from this field. That's basically what an emission factor is, and of course that can be applied to wetlands, to forests, if it's a given hectare of land, how much emissions and so forth. Does that answer the question?
I think so. Thank you. If
Cool.
not, we can add some detail in the community platform after.
Great. So I realize I'm probably going a little, maybe I need to pick up the pace, but yeah, well, I'll at least touch on these examples. So remote sensing, in my view, is a super valuable tool. A lot of the estimates are only kind of loosely based on measurements, have a fair amount of error. We don't always know where facilities that might be emitting are, and we don't always know what types of equipment are present, which can be helpful in doing even emission factors correctly or accurately. It can be really difficult to make measurements on the ground. It just takes a lot of time. And satellites, and as long as you've got permission, airplanes can see just about everywhere. So we've an example of remote sensing being extremely valuable for emissions estimation and tracking is there's work by the Climate Trace Initiative on using satellite imagery to keep track of smoke or steam plumes from cooling towers from different types of industrial facilities, maybe they're power plants or factories. And this is a computer vision based approach where you can say pretty well if there's a certain amount of steam coming out of a power plant, then it's probably emitting a certain amount of carbon dioxide. And you can figure out those relationships by comparing it to power plants that do have continuous emission monitoring systems and so forth. So this is a way that one can use computer vision, in this case, machine learning. They use gradient boosted trees and convolutional neural networks in this case to estimate emissions from power plants and also some industrial facilities anywhere on Earth, even if they don't have measurements directly. What about finding invisible methane? Methane is an invisible greenhouse gas to the naked eye. Historically, it's been common to use infrared cameras, which can see methane reasonably well, or sort of handheld wands, which are able to sense methane enhancements. You can use trucks, continuous monitors, but I'll really be focusing on aircraft and satellites that use reflected sunlight. There are other types as well, but those are the ones I've mainly been working with. Turns out if you fly airplanes or satellites over large areas, there are very large emissions that were not really previously understood to exist in the scale of tons of methane per hour, where previously 10 kilograms per hour was considered big. So I should say remote sensing is possible for other sources of other greenhouse gases. Carbon dioxide, it's a little harder to see, so it needs to be a bigger emission than methane, just essentially because methane is a more powerful greenhouse gas than carbon dioxide. That's basically the reason there. F gases, thankfully, are generally emitted in small enough quantities that it's hard to find them with remote sensing. And nitrous oxide is usually pretty diffuse. It's sort of agricultural. It's hard to measure individual point sources with remote sensing. But this is some of my recent work, which is available as a preprint right now and currently under review, that takes aerial surveys that are quite comprehensive, covering more than 80% of production in most of these regions. And these blue dots and red dots are emissions that were detected, and the black are just oil and gas wells. And what I've found is that in many cases of order 1% of sites are contributing 50 to 80% of total emissions. This is even more skewed than was previously understood. It really indicates that we can have a significant reduction in greenhouse gas emissions and methane emissions from the oil and gas system by getting a handle on a relatively small fraction of sites. And satellites, those can look anywhere. There's quite a few methane sensing satellites that are already up in orbit and more to come. But the big question facing many is, do they work? So my colleagues and I went out into the field and released a whole lot of methane into the atmosphere while the satellites were passing overhead. And this was liquefied natural gas going through a big heater trailer. We were releasing over there. We were safely over here with our wind meter. And turns out these satellites work pretty well, at least in the ranges that they say they will. So we gave everybody about 4 tons per hour, and the results, and these are estimated sort of emission plume shapes overlaid over a standard background. 5 different satellites, 5 different teams analyzing the data from these different satellites. There's not enough time to go into detail, but my takeaway is that these satellites basically work. But there are a lot of questions that come up. So if we're looking at Sentinel-2 data from this KROS, analyzed by KROS, you can see if we just look at the raw retrieval field, the raw methane enhancement estimate, then there's this big enhancement over here. What's that? Well, it turns out that's a farm, but it's not actually emitting methane. So it can be figuring out, well, that is a methane enhancement, but that's not. Can be that there are challenges there, and it is possible to have false positives. And how am I doing on time?
You have about 10 minutes.
Oh, cool. I got a little time. Good.
And there's quite a few questions. Just
yeah. So I want to. I'll breeze through the last bit. Remote sensing can help us map a bunch of infrastructure, know where to look. There's a wonderful database of AI-powered remote sensed infrastructure that might emit methane coming out of Stanford University and the Environmental Defense Fund, including Jeremy Irvin. It's been a major mover and shaker on that front. AI can help with gap filling in data that have a lot of gaps in them. And there's a lot of room for improvement in methane emissions tracking, not just methane, but really all greenhouse gases. Remote sensing can help us find potential emitters, detect active emissions. Machine learning can help us automate greenhouse gas remote sensing. And there's so much work, in my view, that really needs to be done on F-gases, nitrous oxide, hydrogen, heavier hydrocarbons. And with that, I'll thank my collaborators and funders, and I look forward to your questions.
Thank you very much, Dr. Evan Sherwin. That was really, you covered a lot of ground, which is in part reflected in the variety of questions that have come up. Just before we go to a longer question, I have one short question for you, which is, could you just reiterate the difference in terms of how long they stay in the atmosphere for CO2 versus methane?
Yeah, so CO2, there are a couple different components to it. So when carbon dioxide is emitted, some of it gets reabsorbed into various land sinks, some of it gets reabsorbed into the ocean, but something like a third of it stays in the atmosphere for centuries to millennia. So a good fraction stays for on the human lifespan, essentially forever. With methane, the half-life is something like 12 years. So that decays much more quickly.
And you showed us some how computer vision can work for monitoring emissions. What about on a cloudy day, or if there's smoke and smog? Does that how does that impact your estimates?
Oh yeah, I will have a preprint up pretty soon on our latest round of satellite testing, which digs into some of these questions. The question of clouds, it's tough for remote sensing of methane in particular. Any water vapor in the air or any water on the ground also will that'll interfere, and it's so there may be a role for especially for sort of background subtraction. What I mean by that is, if you can take an image of a scene both with the relevant infrared frequencies for looking at methane, but also with optical, red, green, blue imagery, then it's possible in many cases to see, all right, well, this is what things on the ground look like, and this is what the clouds look like. And then if it looks in the infrared frequencies where you see methane, if it looks like there's if you see a shape that's the same as the shape of the cloud that you see just with sort of the naked eye, then you can probably subtract that out and just say, okay, well, that's probably not a methane enhancement, or if there was one, we wouldn't be able to see it there, and only look at the place where there isn't a cloud.
Thank you. And when models look at methane, what about the difference between, say, slow and steady sources, but that are still significant, versus, I'm going to say, speedy sources that come out as like bright blobs that are, does it catch both of these situations, the kinds of models that you have?
It depends. The point source sensing technologies, so most of the aircraft and many of the satellites are only going to find methane emissions coming from a relatively small, like a sort of a facility scale area in general, that are pretty large. So if it's and in some cases, as you point out, those could only last for an hour. In some cases, they'll last longer. It's hard to say, but if you're just taking a snapshot measurement, can't necessarily tell. For these slow, steady, diffuse, in some cases, sources, or smaller sources, those may not, depending on how small they are, they may not be visible by satellites or even by some of the aircraft. And one approach that is to estimating those sources, not necessarily individually resolving them and saying, this is a small source from this facility and this is a small source from this facility, but just saying, in this region, there are this many total emissions, or small sources contribute to this much here and this much here. The Environmental Defense Fund's Methane Satellite, Methane Sat, is designed essentially to do that, so that they can see some of the bigger point sources, and we've tested them, they can do it. But also their system is really set up to be able to estimate the overall role of these smaller sources, even if they can't see them individually.
Thank you. With that, I think we're out of time. Thank you so much. And I'm really happy to have had you on the first section of day 2. And now we're going to move on to our next lecture. So I'm going to share my screen.
I'll unshare, and thank you so much, Donna and Dunlin, and to the whole Climate Change AI summer school team. It's so cool to see what you built.
Thank you so much. All right. So with that, initially when I shared the schedule with everyone, oops, hold on. There, okay. I had shown a 5-minute break. We have run a little bit over time, so I hope everyone's okay if we go right to the next speaker. So I would like to, Danlin and I would like to invite Dr. Kasia Tokarska. She is going to speak about AI for monitoring, reporting, and verification of corporate GHG emissions. And Dr. Tokarska is a climate scientist. She has 9 years of research experience. She is kind of her work sits at the intersection of Earth system climate models and statistical climate data analysis. And recently, she's been exploring physics-informed machine learning and deep learning applications. So without further ado, I would like to welcome Dr. Kasia Tokarska to share her screen and lead us through.
Hi, everyone. It's a pleasure to be here. Thanks so much, the CCAI Summer School, for organizing such an event. So the second part of today's lectures are going to kind of be an integral, in a way, follow-up on the previous series, because we're going to talk about how we can use machine learning for emissions monitoring, and specifically in the context of corporate greenhouse gas emissions. How can we report and verify them, and in what cases machine learning may be actually useful? Just a little bit about my background. I do have a PhD in climate modeling, and then I did several years of postdoctoral research followed by industry experience. So I'm happy to answer any questions, both relating to like academia use of, for example, machine learning for various research purposes, but also how machine learning is increasingly being used in industry, especially in the field of climate risk modeling, quantification of climate impacts, as well as emission quantification that we're going to touch on in today's lecture. I've been also a member of Climate Change AI for over 2 years, and I'm a community lead for climate science, which means it's bridging the gap between machine learning scientists and experts and climate science communities, helping them to kind of develop ideas faster together and learn from each other's background. So as we move on, today's lecture is going to focus on those 3 key areas. So the first one is emissions, different emissions accounting methods. And if you're not familiar with any of those terms, hopefully by the end of today's lecture, you're going to know what they mean. So firstly, we're going to talk about scope 1, 2, and 3 emissions that are being defined by the Greenhouse Gas Protocol, which is kind of like a main document according to which a lot of industry players are trying to quantify their emissions. We're also going to talk about a little bit like what's the problem, what are the challenges with estimating scope 1, 2, and 3 emissions, and how can we maybe address this problem. Next, we're going to talk about some methods and applications. So like what are the traditional ways of estimating those emissions? And then we're going to think about machine learning. Can we use machine learning to help us with those emission estimates? And finally, we're going to talk about future directions and like what are the recommendations for selecting machine learning models in that way. So before we get started with all the scope 1, 2, 3 emissions, I just want to understand like the question why we are doing it. So climate change poses physical risks. So you can have different natural hazards being intensified in the future, for example, wildfires, heat waves, hurricanes, drought, sea level rise, flooding, various sort of physical hazards that are causing direct impacts to the businesses. And if we reduce emissions, that's going to lower our physical risk. So on a global scale, that's why we have the IPCC carbon budgets that were mentioned in the previous lecture. There's so many emission reduction pathways because we are very interested in reducing emissions in order to minimize those impacts of climate change. And on the other hand, we also have transition risks, which are more related to like climate policy risk, regulation, liability, market risk, reputation, technology, and many others. And again, in this case as well, if you reduce emissions as an individual player, like as a company, you're going to lower your transition risk. Because if we are in a world where we have a set 1.5 or 2 degree target, so all the companies need to be aligned with those targets, which means they need to reduce their emissions. If you're the only player who continues to emit, it's going to cost you more, right? Because if there's a carbon tax policy, or there's, for example, market pressure that people prefer to buy products that are more sustainable and net zero, it's going to cost your business. So in a sense, this is the key motivation. Why do we want to monitor and minimize the emissions? Is because if we lower our emissions, physical risks are being decreased, and also the transition risk also decrease, because by lowering emissions, we're potentially going to be the leaders in our space in being close to net zero, like having lower emissions than our peers. So this is kind of like a motivation slide to why would we want to account for the emissions, apart from the side that right now, a lot of different regulatory bodies are requiring companies to disclose their emissions. So there's more and more pressure in terms of regulations. You actually have to quantify your emissions, but there's also other benefits in doing so. So if we look at the greenhouse gas emissions by different sectors in the industry, You can see on this graph that majority of the emissions are from the energy sector. And this is kind of divided between energy use in buildings, transport, and energy use in industry in general. And about a quarter of emissions is agriculture and forestry land use. So agriculture is also contributing to a large amount of emissions, including, well, mostly livestock, manure, but also deforestation. And we can see also there's emissions from waste and industry contributing to this kind of total emission pie or emission budget in a sense. And if we look into like a specific company, what they need to, everybody is trying to quantify is like what this kind of scope 1 to 3 emissions is for a given company. So just as a very brief introduction, scope 1, which is this arrow here, is your direct emissions. So if you have company vehicles, you can kind of measure how much emissions directly you contribute. Also, if you have some company facilities, maybe you can like directly measure it, like how much this facility is contributing to emissions. So that's relatively easy. Then you have scope 2 emissions, which is indirect. How much electricity you purchased for heating or cooling or for your own use, and how much emissions is related to it. So that's also maybe relatively easy to quantify because you have your energy bill, you know how much energy you used, and you know what's your energy source. So if all your energy is renewable from like a wind farm, that number is going to be very low or close to zero, right? If all your energy comes from a coal company, or like it's based on the coal, the electricity comes from a coal factory, then of course this is going to be a high number, and then you can kind of use conversion factors to quantify what's your scope 2 emissions. And then the most challenging bit is scope 3 emissions, because scope 3 emissions is basically also indirect emissions, but everything else that scope 1 and 2 doesn't cover. So here you have both kind of upstream and downstream emissions illustrated by those two cycles, which includes a lot of various activities, including like business travel. So if your employees are traveling, you kind of can quantify how much carbon footprint it has, employee commuting, how much your waste is contributing to emissions, transportation of distribution, whether it's by shipping or by some other vehicle fleets and so on, as well as like how much you're contributing like kind of like upstream and downstream. So how much emissions you're making other people kind of emit for like various investments or use of salt products and so on. So as you can see, this picture of like quantifying companies' emissions can get very complicated very easily because there's so many categories. And for some of them, you might have a very good data, like scope 1, maybe scope 2, but some of those from scope 3, like how much your investments are causing emissions, might be quite hard to quantify. So knowing that like it's relatively easy to quantify scope 1, scope 2, much harder scope 3, which ones of those 3 scopes is the biggest contributor to your emissions? Well, if you think about which of those pots of emissions are the biggest, generally for most companies, scope 3 emissions are going to be the biggest source of emissions because they have so many categories. And usually if you add them all up, they are like significantly higher than your scope 1 and scope 2. It also depends on the company type. So if it's like a very upstream company, like let's say a coal factory generating energy, then there might be a bit different ratio. But like in general, like for most companies, scope 3 is hardest to implement, to calculate, and also the biggest source of emissions. So that's where the problem is. Like you want to limit it, but you don't really know where those emissions exactly are. So here's like a more formal definition. And again, this comes from the Greenhouse Gas Protocol, which is a document that kind of explains all those different emission types, emission categories, and how you should quantify it, given like various options and various examples. So just to summarize what I was trying to say on the previous few slides, we have direct and indirect emission sources, and we have scope 1 emissions, which are direct. So they are like directly owned by the company, and you can relatively easily mostly kind of estimate how much they are. And then you have indirect emissions, which are much harder to estimate, which is scope 2, your purchase kind of electricity, and then scope 3, everything else, basically both upstream and downstream. So here's an example. Like imagine you are running an ice cream company. You call it Earthly Sweets. It distributes ice cream to different supermarkets. And then you want to calculate like what's your total emissions as a company. So what's my scope 1, scope 2, and scope 3 emissions? So let's say you go for your scope 1, you have a fleet of 5, like several vehicles, like let's say you have 5 vehicles to distribute your ice cream. You are heating the offices based on the offsite boiler, so it's direct emissions. And you also have some emissions from the refrigeration equipment used to cool the ice cream. So these perhaps are like relatively easy to add. And again, you can calculate it as the CO2 equivalent units of emissions. So let's say per year, this is how much emissions you contribute just from your direct scope 1 emissions. Then, of course, you need to use electricity, which is in your scope 2, and you know how much electricity you use per year. And this includes like lighting, air conditioning, kind of another energy used for like keeping ice cream cool and storage. And again, like you can convert this based on your kind of like energy provider. So if your energy provider is like a solar farm, maybe this number will be close to 0. But like in this case, maybe the energy provider is using a mix of natural gas and some other electricity. So you do have some emissions in your scope 2. And then you have your scope 3 emissions, which is those multiple categories we had seen before. So just like for an example, let's say you have some business travel because you go to ice cream conferences. You have some emissions from employee commuting to the office, and you also have some emissions from production and transportation of the raw ingredients used to make ice cream. And as you can see, if you add these and those additional scope 3 upstream and downstream categories, you're going to end up with like far bigger number than scope 1 and 2 combined. So your total emissions will be a sum of all the scope 1, 2, 3. And this is important exercise for 2 reasons. So firstly, if you know your total emissions and also your total emissions per scope, you can kind of compare yourself to other peers in the industry. So let's say you can compare yourself to other ice cream companies and say, oh, how are we doing? Maybe our scope 1 emissions are much bigger than peers. Maybe we should switch our fleet of vehicles to electric cars or something else. Or maybe you can see your scope 3 is much too higher, and then you need to like limit your business travel, some other things. So it's really good for benchmarking, and then also for developing those different mitigation measures and like net zero strategies. So like if I want to be net zero, I know most of my emissions are here. What categories can I tackle to bring them to 0 or as close to 0 as possible? So here, what we can see also, if all companies do that, well, in the end, scope 1 emissions of one company are going to become scope 3 emissions of another company. So basically, in a global view, if everybody computes scope 1 to 3 emissions, it's kind of going to be a bit of double counting, right? Because scope 1 emissions are your direct one, and then scope 2 is like how much energy you use. But then the energy company also is like kind of like, you know, measuring the emissions differently. And then scope 3 emissions is how much emissions you contribute forwards, like upstream and downstream. But those scope 3 emissions are also someone else's scope 1 emissions. So here's like an example, again, from the greenhouse gas kind of like reference guide, showing you, for example, like a mining company, power generator, utility, and end user, and how like the different scope 1, 2, 3 are kind of interconnected. So in principle, if everybody calculated emissions the same way and using the same method, you would be able to kind of cross-reference that like emissions from scope 1 here are someone else's scope 3 and so on. However, of course, the real world data is a lot more messy because there's different methods to calculate those different emission types. And those numbers don't necessarily add up, and sometimes they're quite different. So there's a lot of room for improvement. And that's why maybe the traditional methods are limited, and maybe there's a room for machine learning to help with some of those kind of bottlenecks. So just an example in terms of like various industries, and this figures from the MSCI kind of website, you can see that usually emissions, especially for scope 3, can be kind of, and for different scopes, can be in those different kind of sectors. So like energy sector, healthcare, financials, and so on. And you can see the distribution of scope 1 and 2 and scope 3 emissions and like the various categories. So like this is all the blue ones are scope 3, including the orange, scope 3 orange. So you can see the different categories, which we saw from the scope 3 emissions, contribute majority of emissions for most sectors. Only for maybe the utilities, scope 1 and 2 are kind of half of emissions, and the other half is scope 3. But for most of the other sectors, you can see scope 1 and 2 are like about 10 to 20%, and about 80% or higher is like various categories of scope 3 emissions. So that's why there's like a huge interest in like quantifying specifically the scope 3 emissions more accurately and across more different companies. And again, like there's like various traditional methods of emission accounting, and this is just one example, again, from the Greenhouse Gas Protocol. You can find lots of different examples there, how to quantify, for example, emissions from purchased goods and services. And again, it's not easy because purchased goods and services is like a very broad category. You need to think about your like life cycle stages, like what are the different upstream emissions, what are the suppliers' emissions, and there are different methods. So you can use like a supplier-specific method. If you have supplier-specific data, you can use a hybrid method. If you have various sorts of data, average method, like spend-based methods, so like how much do you spend, and then you convert your spend amount of money into emissions. So as you can see, just to quantify one category, of scope like 3 emissions, for example, there's various methods. And like the reason why there's various methods is because sometimes you only have the spend-based data. For example, you only know how much you're spending on this thing. You don't know anything else. Sometimes you might know a lot more, like the supplier-based emissions. So that's why, well, the more data you have, the more accurately the answer could be. But also because of this variety of different methodologies in quantifying the emissions, there's a variety of answers because various companies, they use certain methods for different reasons. So here is an example. Like in a sense, if we think about, can we use machine learning for emission estimates? So the idea here is to make use of already reported emissions from various industries in various sectors. And those can be found, for example, it's called CDP database. That's one source. There's also other sources of emissions where you can see different companies report the scope 1, 2, 3 emissions and the different categories of those different emissions. And you can make inference on emissions for a known company X in a given sector, for example. So this is kind of like an idea I'm trying to illustrate what machine learning can be used for. And then also we're going to talk about how could it be limited. So let's say you know one company, it's a food company number 1, and they reported in this CDP database scope 1, 2, 3 emissions. And like they kind of show the different numbers, right? And then you're food company X. And you're like, okay, we're also a food company. So let's assume the machine learning algorithm can infer. So our scope 1 are similar to scope 1 of this company. Our scope 2 would be similar to this. And our scope 3 would be similar to this, right? And then let's say you have more data sources. So you have company 1, 2, 3 that disclose it. Then you can use some sort of clustering algorithm to infer your emissions. So like, because of my peers, like they have these emissions, I probably have similar emissions, right? So in principle, it makes sense. But it can get complicated quite easily because like assume one of those companies is a large international company and you are a small family-owned store. Well, then your scope 1 emissions are not going to be the same as this large international company, food company, right? Again, scope 2 might be quite different as well. And scope 3 definitely will be very different. So like the size matters in a sense, like how big the company is, how big is the revenue. And that's why the clustering algorithm kind of need to be constrained by some things. Like it needs to be aware of like, what are the key things that I need to know in order to identify the right features and do the interpolation or the kind of the predictions using the right kind of predictors. And likewise, again, like maybe the first food 1 company is a large international company in California, USA, and you are a small family-owned store in Finland. Like they would be very different, especially for scope 2 emissions. Probably maybe the energy use is very different. They use more air conditioning, you more use heating in the winter. Scope 1 might be very different because of the size. Scope 3 might be also very different because of the upstream and downstream emission categories and their kind of composition. So again, like even if you were to kind of develop some sort of clustering algorithm using this data that is already disclosed for various companies, for the various sectors, for the various kind of countries that operate, different sizes of the kind of companies, it becomes quite complicated very easily, getting numbers that actually make sense, right? And so that's why for maybe more accurate predictions, some of the methods would use additional attributes, such as like country of the headquarters, number of employees, company revenue, size, and so on, right? So you want to find like a peer company, food 1 company, that's as similar as your own company. So the algorithm might be looking, okay, can I find a company that is operating in the same country of a similar size, similar revenue, similar structure, similar sector, right? And then this kind of emission predictions may be more accurate. And why are we trying to do it? Well, this is to, again, like to estimate maybe scope 3. So maybe you're a really big company and you don't know how to easily quantify your scope 3. You can quantify only 2 categories out of all these 15 or more categories of scope 3 emissions. And you know some of your peers quantify more. So you kind of want to know like, what is the approximation of my number, right? But again, like you have to be very careful how you do this mapping because you can get like very different results depending on your kind of like inputs, right? And what is also really important is to be aware of the data biases in the database itself, right? Because the CDP database is just one source of data. That's where a lot of companies disclose emissions, but not everyone, right? Like, so I think there's like about, I know, like over 6,000 companies that disclose emissions, but a lot of them are like very similar to each other. So maybe if you're one of those type of companies, then your prediction will be quite accurate. But if you're a completely new company that only like has 2 or 3 peers in this database, this prediction will not be as accurate. And again, there might be some other biases in data because only certain companies disclose emissions and therefore like the algorithm only has a limited sample of data to learn on. So it's really important to kind of understand the limitations and also kind of like the uncertainty in this prediction. Like, does it make sense? And are the numbers kind of in the order of magnitude or like similar to the numbers you would expect? So like doing some sort of cross-validation. And there are several papers that were recently published over the past few years that tackle this issue of emission prediction, especially for scope 3 emissions, but also for scope 1 and 2, using various machine learning algorithms. Like, I'm not an expert in like this sort of methods, but I was really interested in knowing how we can use machine learning to arrive to maybe more accurate answers, especially for scope 3 emissions, which are so difficult to quantify. So one of them is boosting methods. And as you can see here, there's like different features that are important for predicting each category of scope 3 emissions. And the features may differ. So here's a graph of feature importance. So this is when you want to like maybe evaluate your machine learning algorithm. This feature importance map will tell you what features are most important, right? And again, like here we can have like scope 1 to 3 emissions, but also like how a number of employees and all these other things, like what is your industry, how much cost you have, what's your net property value, and so on. Like, so lots of various industry specific data. And then you can see which of those are really important to predict each of those categories of scope 3 emissions. So this is like your scope 3 emissions at the bottom that you're trying to predict. So you can see that like the yellow one is really good. So it means like scope 1 emissions are really good predictor for some of those, right? But not as good predictor for some other of these. So I think it's really important to kind of get this sort of idea in terms of like what features are important, what can we predict confidently, and what can we predict maybe less confidently. And this paper was, it's called like Machine Learning Models for Prediction of Scope 3 Carbon Emissions, which is from the Harvard Business School working paper. And I will provide links to all the papers discussed in this lecture by the end of this presentation. So I think looking at this, we can ask ourselves a question, like, does it make sense to use different category features for each individual scope 3 category? So should we be predicting all these different categories of scope 3 emissions, or should this be just maybe one number, scope 3 emissions, and like finding which predictors work, right? And then also, what are the pros and cons of doing it? And again, there's no one right answer. It really depends. Like if you use different algorithms, like here they're using AdaBoost decision tree regressor, but they also compare various other kind of algorithms in predicting it. And some algorithms prefer better than others. And sometimes having this granularity of predicting different categories of scope emissions is good. But sometimes you might get like kind of unrealistic results, right? Because you have so many categories that maybe are not necessarily correlated to any of those things here. So again, like designing your algorithm and like thinking like in a way, what should it be here versus what should it be here is very important. And again, like the one way to maybe start thinking about it is like start simple. So like think about like what are the most important features you think would be important, which probably is like maybe country, company size, like the things we discussed earlier, and then like keep adding additional things and like see, does it actually help or hinder the results, right? Like, and if you can think of a reason, oh, I think industries should be related, right? Companies in the same industry should have similar emissions, then maybe it's a good reason to keep it. So like really kind of not only using the machine learning as a black box, but trying to see which features are important for what reasons, and do those reasons actually make sense. So just another example, and this one is from the Han et al. 2021 paper, which is estimation of corporate greenhouse gas emissions via machine learning, that was presented at the ICML 2021 conference by CCAI as well, in the CCAI session. So they here also develop like inference-based methods for scope 3 kind of emission prediction. And again, you can kind of like use a lot of different features, including like ESG data, which is like another data source, like similar, like CDP is only emissions. ESG data source will give you additional features, such as it's like environment, social features, and governance features. So you can see like how does the company score in all those different dimensions? What are the different financials of the company? What's the classification in what industry it is, right? So you can use different features and then like kind of like use, again, feature engineering, trying to figure out which features are most important. They also use some data augmentation and adding mask data, like just to make sure that they can kind of like see, does the algorithm actually predict the right things for the data we know of, but we're not going to tell the algorithm to use it. And then they kind of come to the different final distributions. And you can see that like, calibrated versus recalibrated, there's like a difference in prediction of actually scope 1 emissions shown here, but they also do, I think, scope 3 from what I remember. So in this paper, they identify common challenges So the first one, which we kind of already mentioned, is imbalanced data sets. So again, maybe the CDP database only contains like specific type of companies, but not other type of companies you're interested in predicting emissions. Again, the ESG data sets are very varied. So like depends on the data source you get, the numbers might differ. And all those different kind of features and your input parameters might really adjust, like, might affect your results, and sometimes it's for the wrong reasons. You can also have like missing features. So if you have an algorithm that strongly depends on, like, let's say one feature that's really important, but not all companies disclose it, then it might be kind of difficult to train your model on features that are only disclosed by very few companies. So it's also good to have like features that are generally known and generally disclosed, because then you can kind of train a larger sample of models. You can also have mismatch feature patterns. So like maybe sometimes there's a mismatch between what feature it is. And there's a huge need for uncertainty quantification, because just running any of those models, you get like an answer for scope 1, 2, or 3 emissions. But what is the plus minus number on it, right? So if you run a different algorithm and you get a completely different answer, right? Like you want to be able to kind of quantify within like a specific range, maybe like using a different amount of features or so on. Like how can you quantify the spread in your results? Because your results should not be just one number. You should be quite confident, like, okay, the predicted emissions are this much, but like the range around this number is plus minus a certain amount of percentage, for example. There's another paper that specifically focuses on scope 1 emission estimates, and that's also using tree-based machine learning methods. So again, you can see that like here the target variable is scope 1 emissions, and again they use different predictors like economic theory, prior studies available, different data available, and different data sources. So there's also Bloomberg terminal that provides relevant data that can be used for training, UN treaty collection, climate change database, and they again, like they try different kind of algorithms to build the models, and then again, like model evaluation is really important as well, which means like compare different models, compare different architectures, and like see how much difference it makes, and then also try to explain, can you actually explain this difference? Why one model is way different than the other? Is it because of the different predictors, or is it because of some reason you can identify to help you know which machine learning model to use? And the reason why I'm giving so many different examples is because it's a very emerging field. Like I think there's a lot of value in like being able to predict scope 1, 2, or 3 emissions from the data if you don't know your own answers, or if you want to estimate someone else's answers given certain features. But also because it's such a new field, there's like so many answers right now and so many algorithms. So it's really important to be very critical about it in terms of like what is actually the uncertainty around those projections. So this kind of brings us to like general overview of the uncertainty and like also opportunities and challenges in using machine learning for emissions inference. So these are a few questions you might want to consider. Like, for example, what are the main benefits of this presented methods and others, right? And then what are the main drawbacks? Is there something missing we could account for? Can we trust those inferences? And what are the alternatives? So I think in this lecture so far, like I briefly kind of caught on those ideas, because I think the reason why we're trying to do it is because it's really difficult to calculate it using the standard method. Some of those emissions are really difficult to quantify, or you might not even have the right data. You just kind of get your product. You don't even know really who the suppliers is or like what the supplier emissions are. So it's potentially very important to be able to quantify in different ways. However, because of the variety of methods and the variety of data sources, there's a lot of uncertainty in these predictions. So we need to be very careful how we actually report it and how we trust it. So doing those different kind of interpretability tests and such as like feature importance and like also uncertainty quantification is really important. So just having one model giving you one number might not be really trustworthy, but if you can kind of run an entire like uncertainty quantification around the different algorithms, and you kind of can see which algorithm performs the best and for what reasons, there might be more trustworthy results. And I think if we talk about like recommendations for selecting machine learning models, like what are the additional dimensions that need to be considered in evaluating the methods that are not shown here? So I think the two key dimensions you might want to think about is the potential impact. So how much impact can you have? Like, is the result much better? Is like the error much smaller? And then also like how difficult is it to implement it? Because if you have an algorithm that really performs very well, but it requires a lot of features, and those features are really difficult to collect for most companies, then it's going to be maybe not as useful. If you have an algorithm that kind of feeds on some key data attributes that generally performs well also for your prediction, that's probably a really good model. So just like thinking in terms of like the impact, like is your impact good in a sense? Can you show predictions that are kind of robust? You always get the same number with small uncertainty range about it. And then like, is the difficulty relatively maybe easy to implement, or even if it's difficult to implement and it has a high impact, is it feasible to implement? Because ideally you would like to implement it for a range of companies, and keeping in mind that like the data reported sometimes varies widely. So you want to maybe narrow down the amount of features you use to like the most commonly disclosed ones. So again, there's like emission data landscape. So here's some data sources and the papers discussed in this lecture. So this is the key 3 papers I discussed, and a lot of more coming up or like recently published. So if you're interested in this topic, it's a highly kind of like, you know, a hot topic right now because everybody wants to do it in different ways. The key database for emissions, like scope 1, 2, 3 emissions officially disclosed by the companies is the CDP database. There's also the greenhouse gas protocol methodology, which kind of explains you what the scope 1, 2, 3 emissions are and how to calculate it in different examples. And again, there's like a variety of methods depending on what data is available. You might be also interested in like science-based targets website, which kind of also has ways of quantifying emissions, especially in the future. And so kind of like going between now and the future, like when you're net zero by 2030 and 2040 or 2050, how would you quantify your emission evolution between now and those future years? So I think, yeah, this lecture is pretty much just a brief intro to like how machine learning can be used for quantifying corporate emissions for scope 1, 2, and 3 emissions. I'm happy to answer any questions if you have.
Thank you so much, Kasia, Dr. Tokarska. There's a lot of questions on the community platform, and I'm going to group some of them together and ask them to you to give you a chance to kind of round out the lecture. There's, okay, let's see where to dig in first. Can you, before we get started with some of the questions, can you clarify something that you brought up, which is how you allocate emissions to either scope 1 versus 2, and then how the overlap between scope 3 and 1 and 2 works. If you could just go back, there were some people asking about why is there double counting, or where does that double counting mean?
Yeah, sure. Happy to share that slide again. So for a given company, those categories are unique. So for one company, if you're a company producing ice cream, or your scope 1 emissions will be different, scope 2 emissions are a different category, and scope 3 is a different category. So your total emissions will be sum of all these. But just if you think about it, like for example, so scope 1 is very direct, right? Like you drive the company vehicles you drive, you can directly quantify the emissions. And also like, for example, your facilities, like how much emissions they produce, like you can measure it. But then like for scope 3, it becomes more difficult. So like if you consider, for example, business travel, how much you travel, right? Like you can kind of quantify it and as your scope 3 emissions. But then let's say if you're an airplane company, that could be maybe your scope 1 emissions, because this is how much emissions you produce, right? Like, so in a sense, like someone else's scope 1 emissions might be your scope 3 emissions, because especially scope 3 emissions has so many categories. So some other company that produces it would be using it like a scope 1 emissions, for example, which then you also disclose it as your scope 3 emissions. So just to clarify, scope 1, 2, and 3 emissions are unique numbers for a given company. But then globally, all we need to, if everybody was disclosing like 100% exactly, all you need is scope 1, and scope 1 pretty much like emissions, and then like scope 2 emissions will be like how much energy you purchase, right? But then like the company that kind of like produces the energy would also disclose this as their, for example, scope 3 emissions. So in a sense, like they are interconnected, but for a given company, you need to disclose all 3, because for yourself, they are all unique, if that makes sense.
Mm-hmm. Thank you. Yeah. And my scope 1 will never be someone else's scope 1. However, my
that's
scope
your
3 will be someone else's.
It's your direct emissions, yes.
Great. So there are about 4 questions that are all circling around this big, this one big question that people want to know, which is how are companies and or governments really either incentivized or motivated or mandated to measure and to report? And how do we trust those numbers? Is there any mechanism in place for checking them?
I mean, these are great questions. And just maybe just to clarify, like I'm speaking from my personal experience, just like working with those different data sets. So what I'm going to say is like my personal opinion, what I think. So firstly, like there's two key motivations the companies might want to do it. So firstly, it's regulatory basis. So there's a lot of climate regulation coming in, and it's very sometimes region specific. So the EU has its own regulation, US has regulation. There's some global regulations, for example, TCFD, so the Task Force on like climate disclosures, right? Like, and all of them require you to disclose your scope 1, 2, and 3 emissions. So that's what it says. And then how do you disclose it? Well, then you say, okay, I want to disclose it because I want to meet this check mark. Then you go to the Greenhouse Gas Protocol, which is kind of like the international methodology document for how to disclose it. But again, it's not as simple as we were discussing, because there's different ways to quantify it. And especially because different companies might have different data. Some company only has, oh, this is how much I spent for different categories. How do I convert dollars into emissions, right? Versus some other ones might have more granular data that you can quantify more easily, like the different emission sources that Ivan was also talking about, like CO2, non-CO2, and then you put them together into like the CO2 equivalent sources. So there's a lot of regulatory pressure in order to do that. How accurate those answers are, well, again, this is yet to be verified, because I mean, step 1 is like get everyone to do it. Step 2, help everyone to improve it, right? So right now we're in this like step 1, like let's everyone do it and like do the best you can, even though we know some people might do better job than others, and like also some industries are a lot easier to quantify than others, right? So just keeping in mind, it's not only like companies not wanting to do it, but it's really hard to do it if you see all those categories. And secondly, like, so once we get like to everyone disclosing it, I think it'll be much easier, like having this data to see like the data gaps and like also, okay, well, this sector has a very large spread in emissions. So maybe there must be like a clearer methodology communicated to them to help them be more in line in terms of how to disclose it. So I would say, again, like get this data, I mean, CDP database, they do have some quality control, like you have to disclose specific emissions and justify it. But again, sometimes it's not really apples for apples, right? Maybe apples for oranges, because maybe somebody discloses all scope 3 categories, somebody else only discloses business commuting as the scope 3 category. So like, because they can't quantify all the other ones. So it's really just being aware of those different data gaps and like, kind of like what you see, just like first evaluate what this data set is. Can I use it directly into my machine learning, maybe like my algorithm, or can I, or do I need to clean this data first? Maybe I want to select companies that disclosed only all scope 3 emissions, right? Like if somebody only disclosed one category, maybe I don't want to use this for my training. So it's really just being kind of prudent how you use this data. Again, it's data, it's not going to be perfect, but like just assuming like this is as good as we can get, like how can we make the best use out of it? So that's first reason, like regulatory pressure and like companies start doing it. Second reason is peer kind of pressure, in a sense, and investor pressure, right? So in some certain industries, like whichever industry you consider, if you want to be the leader, you want to be the first one to reach net zero, or you want to be one of the first companies that reach net zero target in 2030, 2050, well, you want to be disclosing those emissions, and you also want to show that whatever you're doing is making those emissions smaller and smaller year on year. So in some ways, like let's say you don't disclose your emissions, but then you notice all the customers actually end up starting to only purchase from the companies that are like labeled as sustainable, and then they disclose emissions and they have a decreasing trend. So right, like, so there might be a lot of market pressures, like peer pressure, investor pressure, making you firstly disclose it, and secondly, making sure that there's this kind of declining trend that you're going towards net zero, that your emissions are actually declining over time.
Thank you so much. And I know it's a big question. There's a couple of related questions to that, a few. So here we go. We'll just dive in. First of all, if you hold on one sec, I'm just scanning them. So you did talk about the data. So, okay, first related question. There was a process pitched in an article in the Harvard Business Review that someone mentioned. I'm not sure if you're familiar with it, but it was an article that came out in 2021, I think, in late 2021 by Kaplan and Romana. They proposed an alternative accounting scheme assigning e-liabilities across the value chain. Are you familiar with that article? And can you comment on if it would solve some of the issues that you brought up?
Yeah, well, thanks so much for bringing it up, and like possibly please also paste the link to it so other people can also have a read. I don't think I have read it specifically, but I'm aware of several other schemes as well. So I think where we are right now, we're in this kind of place where a lot of people are familiar with the Greenhouse Gas Protocol methodologies for scope 1 to 3 emissions. They started disclosing it as mandatory. And of course, there's going to be emerging methods that are like way better and like, oh, this method is maybe more accurate for this or that. So I think there's a lot of value in trying to figure out like, what can we have better methods to disclose it? But also there's a challenge then like in implementing those methods to be regulatory mandatory, because right now you've got everyone to get scope 1 to 3 emissions the traditional way. So I think it's a bit like maybe we need a bit more time, and maybe like if the method is really performing very well across all the scopes of emissions, then like it will require some time before it's like required to be used for the different industries. But again, like we're very early on in this kind of emission quantification space. I think it's really valuable in a sense to be working with both the existing data, existing methods, and seeing like how can we make best use of it in the near term, but then also like trying to develop better metrics in the long term, and hopefully they become mandatory if they're like truly the better metric.
Yeah, and so you were talking, when you're talking about machine learning, I mean, uncertainty, there's different sources and kinds of uncertainty, but here we know definitely there's uncertainty baked in because it's self-reported data. And can you give examples of how you, like, given that you don't have a entire confidence in the sources of your data, how do you sort of ensure the model is as good as it can be given the data you're starting with?
I think that's really where the machine learning experts can jump in like with ideas, because I think that's exactly like what we want to be doing. So there's two things. We don't want to treat the data as like the ultimate source of truth, and we don't want to treat the model as the black box model that does magic and outputs numbers, right? So we want to know both, be critical about the data source you use, and like run some sanity checks on it. So for example, the CDP database, you can kind of see like what's the maximum number of emissions. If somebody discloses a number that is bigger than the total global emissions, then of course, you know, it's like outlier you don't want even in your data set because it's not feasible, right? So just kind of having like some sort of sanity checks, like what's the maximum number? Do you want to keep the outliers in, or you assume that if someone's number is way bigger, then you just don't treat it because maybe it was like some sort of conversion error. They didn't calculate greenhouse gas CO2 equivalent. They calculated some other unit, for example. And again, like the database itself, like they try to do some preliminary checks, but of course you still might end up with some sort of errors just because there's like so many conversions needed, like additions, right? Like it can easily get messy. So having sanity checks on your input data is really important. And then secondly, understanding kind of what the model does, right? So if you get some results and you like, I think like the feature importance is really interesting, or like some other interpretability, like this entire field of like AI interpretable methods, where you can kind of figure out like what the model is learning from and why. So you can kind of see, is it learning from the things it should be learning, right? So as we discussed, probably the company size, like country of origin, like these are the common features that everybody uses that are really important. And if your model makes predictions based on some other very minor features, maybe then it's not as robust. So it's just really kind of using both like critical thinking and various like trial and error kind of like in terms of different architectures, and like understanding like what works, what doesn't, and why. And I think the 3 papers I presented here, like they do quite a good job in terms of comparing different model architectures, comparing different features, and like trying to make sense out of it. Like, okay, given this, these are the errors for these features for this, should we use this or not? And actually some people would argue maybe too much granularity is not good because you're getting like data that doesn't make sense anyway. So maybe keeping it more high level makes it better, right? So there's like different schools of thought on that.
Yeah, following up on what you just said, there's a question about that. So your lecture really elucidated emissions accounting, but what about methods for just prioritizing or finding out, like a company wants to figure out where can I have the most impact? How do I want to just reduce scope 3 emissions? Are there ways of going about that?
I mean, I think there's like a lot of pressure right now to know your own emissions before you start reducing it, right? Like in a sense, because like you don't want to just have like a rent, like kind of, oh, I kind of want to be net zero, so I'm kind of going to do like electric cars or like the things that generally like get me to net zero. Like you kind of want to know like how much impact it has. So it is like, that's why there's like so much pressure trying to like get the companies to disclose those different granularity of scope 1 to 3 emissions as much as they can. And I think, again, like from my personal opinion, I think there's 2 things you can do. So firstly, we'll do the best you can to quantify those emissions, because eventually anyway, it's kind of required at some point. So you want to get started early, and like maybe the first time you quantify, you only have like a vague idea. Then you kind of know, oh, we need to ask the supplier more, like what sort of like, you know, what their emissions are. And if a given supplier doesn't want to disclose their emissions, maybe you want to switch your suppliers, for example, right? Because you want to be truly net zero. So like, again, like a lot of those measures might not be immediate, but like if you quantify it first and you're like, oh, our main data gap is here, we want to improve there, let's get more sustainable suppliers, or like, let's get more information from the existing ones. So that's the first one. And second one, I think the benchmarking. So again, there's usually leaders in the field that are like already like close to net zero, like really on the kind of journey to net zero. You can like read their reports. And again, in the corporate world, every company or like big company publishes their, it's called like TCFD report, which is like general kind of climate report. And again, some are better than others, but like the really good leader would have very detailed reports talking about the different strategies they use. So if you find like peers in your sector, so if you're the ice cream company, other ice cream companies, what are they doing? Like the most net zero ice cream company, what they are doing. And then it kind of can give you an idea what sort of initiatives you might take. But then again, you still need to know, like, would that actually work? Because maybe, oh, we actually don't use cars, we use something else, right? Like we use bikes. So like having electric cars is not really a good measure for us. So it's really kind of like a mix of those things.
Are the papers that you pointed out, have you, I apologize if you covered this, but there's a question if you found any, do the emission estimates agree with each other? Are they roughly correlated, or, and yes, so
that's a really good question. And I think from my understanding, at least, the papers use quite different input data sources. So I think they don't try to predict the same number. So it's quite hard to compare how good they are across each other, unless you like actually want to like get a code from each of them and like use it on the same input data set to know what the numbers they produce. But I think each of those papers does a really good job comparing different model architectures for the data set input data they use. And they use different input data sets for different reasons. So I think, again, reading the three of them is a really good introduction to like what data is available, what algorithms are generally used. And from then you can kind of like, well, depending on your use case, you can kind of think further, like, how can I make use of it? And how can I improve on that knowledge?
Is AI used, was partly asked at the beginning of the same question, but is AI used to replace existing methods, maybe at the level, like the ground level for an individual company doing their own accounting? Or is it more useful kind of at this next level where you're trying to estimate based when you don't have numbers, for example, or aggregate numbers?
Yeah, so I think I'm mostly familiar with the second method, right? Like it's usually like knowing like if there's a big data set, or like if you want to estimate something you don't know, can you use existing data to estimate it? There might be actually startups in this space also using AI to help you estimate your current emissions. And again, like that might be easier to cross verify, because if you already know your scope 1, 2 emissions, if you already know how to quantify it, then generally you don't need AI, because you kind of just updated the data source and you already know where the data comes from. But like maybe if you're like trying, or like you have a very complicated case in how to quantify some of those scope 3 emissions, maybe some of them you directly quantify, for some of them you use the AI method. So I think it really depends on the use case. And again, I've just been like very transparent about like what algorithms are being used, and like what are the main limitations, and are they using the right way, using the right inputs, like right features, and like the architectures that are recommended for this sort of task.
And are you familiar with an article they're citing? There's an article from The Guardian from 2017, and I'm just going to quote from the question, and which is a quote from The Guardian saying, just 100 companies are responsible for 71% of emissions. Well, first of all, do you know which article this is? And have you heard this before?
I think I might have seen that before. So I think that also kind of shows that like a lot of the emissions come from the major oil and gas players. And again, like unless we have like very strict regulations, right? Like it's going to be quite difficult to like reduce global emissions unless the major players also reduce it. But that should not mean that just because the top player is not reducing emissions, I should not reduce mine. So I think just thinking in terms of like a net zero, and I think the previous lecture kind of also emphasized it, like it's a global target. Like it doesn't mean like just get those 3 people to reduce their emissions. It's actually like, let's develop a system where everyone's emissions are very low or close to zero. So.
Yeah. A little bit of a pivot. We did mention in your intro that you're interested in physics-informed machine learning and deep learning. Do you mind talking a little bit about more what excites you in terms of the PIML applications? Maybe it relates to this talk, or maybe not. I'm not sure.
Yeah, definitely. So I think for this talk, we haven't really touched on it except for like the feature importance, which is kind of more like interpretability techniques. But I think what is really exciting right now is what is this tutorial for these lectures, or actually the lectures on the Climate Science Day. So I think Thursday is the Climate Science Day, and one of the tutorials is going to be El Nino predictions using different machine learning algorithms. And I think if I'm correct, I'm not sure. Last part of the tutorial is actually using physics-based machine learning methods as well. And I think so. My main background is climate science, and I'll also talk more about it on Thursday. But especially if you're trying to predict like physical phenomena like El Nino or like weather or extreme events, there's a lot of climate physics going behind it. So that's where I think physics-based methods are particularly useful, because not only you get like the input data from observations, but you can also constrain it. So like carbon has to be constrained in the carbon cycle, right? Like the emissions in the atmosphere plus land plus ocean, like that has to be equal to the same total. And same, like there has to be conservation of water, energy, and so on. So I think because of the beauty of like a climate physics system, there's a lot of interesting applications in terms of getting results that are more robust. And what I mean more robust is like making future projections more accurate. So it's not necessarily getting accuracy on the near-term prediction, but again, on the longer term, how much long-term can you project into the future? And if you're physically constrained, quite often this projection is more robust into the future.
And that was a nice teaser too for everyone for Thursday. And we hope you join us then. I want to ask you there's a couple more questions if you still have energy and time. There's an IPCC guideline, a 2006 guideline, I think. Is that aligned with some of the protocols and reporting you were mentioning? So the person is asking, can we use AI to calculate emissions according to that guideline, the IPCC guideline 2006? I'm
not entirely familiar with it. I think definitely usually the IPCC guidelines should be in line with like what the kind of industry level standards can, like usually that's the main kind of information that feeds into those standards. But I think because it's 2006, I would like probably recommend revising, like seeing is this guideline updated or maybe expanded on in the most recent report, like 2021 and 2020. And then probably they will be easier to find like connection with it. But in general, like the IPCC methods are like the cornerstone, and like then the industry methods build on it. So it's not in competition.
Okay. And a couple of questions that are about adding features and improving the model. So you did talk a little bit about adding more features to the model, and someone's asked a kind of involved question, which basically is asking, if you add more features with less importance, will that improve the model prediction accuracy compared to one with only the important features? Sorry,
I think that's a great question to test, right? And I think then also the question is like, what is the use case? So if you're just trying to predict your own emissions and you find like these additional features from other data that is making the prediction more accurate, then sure, that's a quick win. But the question is then, if you're trying to interpolate for like various companies that have missing data, and only some of them have these additional features and a lot of them don't, then do you still want the algorithm that only can predict it on like only for certain players of all, right? So it's kind of like in a way a trade-off. Like how, like of course, more data, input data is better, but then like, can you actually get all this input data for various players? And like it depends really on your use case.
Is there a use case? This dovetails with another question, which someone's asking about prediction at the household level. So emissions from energy use, for example, at the household level. Can we use AI for generating kind of like household level inventories?
Yeah, I think so. I think it's a bit different from those scope 1, 2, 3 emissions, which are more like corporate. But I think again, like the methods are quite similar because the household level emissions are like similar to like an office emissions in a sense, plus maybe additional sources of emissions that you have in a household that office doesn't have. So in principle, like the theoretical methods, probably most of them are applicable. The only challenge would be that like this data might be harder to find, because I don't know if it's like households don't really report their emissions as far as I know. But I think there might be some kind of like global top-down data sets that are trying to estimate like what is the household emissions for various countries or in various regions. I don't know if climate trace data set does it, but climate trace is like one of those kind of like top-down ways of trying to, in a way, also quantify various industry emissions, but like instead of like, let's not rely on industry data, like let's see like, can we like use kind of like satellite observations and like kind of like zoom in down to specific regions and sectors, can we estimate it? So in an ideal world, if like your top down and bottom up should add up, right? Like, so if everybody reports emissions, what you observe from space should be the same number. Of course, it's unlikely to be the case because of all these uncertainties, different methods and so on. But I think that's what makes this field very interesting, because whichever way you work, top down or bottom up, there's like a lot of research questions you can answer.
Yeah. And I think that's a great place to end on. Thank you very much. Unless there's anything else you want to add that you think that your thoughts that you haven't had a chance to cover?
Thank you so much for this opportunity. I think these questions were really interesting. So I'm really glad to hear people are very involved in this topic as well. Yeah, definitely the paper links will be shared as well. So feel free to check them out. And also if you know of other resources and papers, and again, like I only presented 3, feel free to comment on there and like share with the community, because it's a very interesting emerging field. So hopefully there'll be lots of innovation going in that. Yeah, and thanks so much to the summer school team for organizing it. It went really nicely and smoothly.
Thank you. Thank you so much. And so for everyone participating online, just a few wrap-up notes. Here, I'll share my screen. Hold on. So just a few wrap-up notes as we conclude today's session. You will receive more information from CCAI summer school organizers on how to leave feedback, to be able to get the slides from today's presentations, and more information on the related tutorial, which will be available today. This will all be on the community platform, and we look forward to seeing you on day 3. So thank you to our speakers, thank you to the whole organizing team, and see you again. Bye.